Hello, my name is Neng-Fa. The paper I'm presenting is about how to encode reachability constraints into SAT and how to use these constraints in modeling and solving graph synthesis problems. Here's the outline of my talk. I will first give an overview of the Picat language and introduce these HCP and SCC constraints, and briefly talk about the set encodings of these constraints. And after that, I will give several modeling examples and present some experimental results. All right. Picat is a Prolog-like language with new features for modeling and scripting. It provides new data types that do not exist in standard Prolog, including arrays, hash maps, and hash sets. It provides new language constructs for modeling and scripting, including pattern matching rules, functions, loops, list comprehensions, and assignments. It also provides facilities for solving combinatorial problems, including tabling for planning problems, and several solver modules for solving constraint satisfaction problems. So Picat is a logic language, but it supports functions. You can define functions in a similar way as you do in a functional language. Although functions, are relations. All right, but for many applications, functions are more convenient than relations, because you don't need to introduce new variables, as you see in this example. Quick sort. Yeah, you divide the list into two partitions and sort them recursively and then concatenate the results. Okay. Picat provides loops. There's a foreach loop, has a very straightforward semantics. For each combination of values, E1 in D1, En in Dn, if the conditions, condition 1, condition n are true, then the goal is true. A foreach loop forms a naming scope, so you don't need to declare what variables are local to each iteration and what variables are global. So it is quite convenient. A list comprehension is a declarative way of constructing lists. So for each combination of values, E1 in D1, En in Dn, if the conditions, condition 1, condition n are true, then T is added, into the list. Picat provides assignments. All right, one type of assignment is like a set-arg in Prolog. And you can also assign logic variables. All right, so with this assignment, you can use a logic variable to hold values at different stages of a computation, so you don't need to introduce new variables. Picat provides several solver modules for CSPs, including SAT, CP, MIP, and SMT. All these modules follow the same interface. The interface offers domain constraints, arithmetic constraints, Boolean constraints, table constraints, and global constraints. All right, this is very similar to a typical ICLP'21 language. And the built-in solve, is used to label variables, to satisfy constraints. You can also describe objective functions to minimize or maximize an expression. In the latest version of Picat, there are several global constraints, named HCP and SCC. The HCP constraint takes well, 3 arguments: VS, the set of vertices; ES, a set of edges. Okay, each vertex, all right, comes with a characteristic variable, vi. Okay, bi. So bi is 1 if and only if, okay, the vertex is in the subgraph. And each arc vi, vj, okay, also comes with a characteristic variable bij. All right, the variable is 0 if the arc is not in the subgraph, and it is 1 if the arc is in the subgraph. And the argument k indicates the cardinality of the subgraph, number of vertices in the subgraph. So the constraint HCP is satisfied, all right, if the subgraph forms a Hamiltonian cycle. All right, the variant HCP grid, okay, is for grid graphs. So a grid graph is represented by 2-dimensional arrays of 0 and 1 variables. The SCC constraint is similar, okay, but it is true if the subgraph, okay, forms a strongly connected component, and it has a variant named SCC grid for grid graphs. All right, these constraints are encoded into SAT. All right, Picat uses an encoding called distance encoding for HCP. All right, the detail can be found in this paper published in last year's CP conference. So the distance encoding is pretty simple. So giving a graph, okay, so if k is greater than 0, if the subgraph has at least 1 vertex, then it chooses a vertex as a start, and the start vertex has distance 0. If there is an arc from vi to vj, then vj's distance is the successor of vi's distance, unless vj is the start. So there are several ways of encoding the success function, all right, in the paper. It compares 3 encodings for the success function. And for the SCC constraint, Picat uses an encoding called tree encoding. All right, the idea is similar. Okay, so for a subgraph that, okay, non-empty subgraph, it first chooses a vertex as the root, and the distance of the root is 0. And it chooses a vertex as the parent for each non-root vertex. Okay, and if vi is the parent of vj, then vj's distance is the successor of vi's distance. Okay, it is very similar to the distance encoding. All right, now let me present several examples, okay, taken from recent logic programming contest. All right, the Roadrunner, Masu, Shingoki, and Tapa. You can find the complete programs on my GitHub account. In here, I'm going to present 2 programs, one for the Roadrunner problem and one for the Tapa problem. The Roadrunner problem goes like this. So giving a grid map where white cells are free and black cells are hills. The task is to install laser kits on some of the white cells such that no 2 laser kits can shoot each other. A black cell may have a number that indicates the number of laser kits installed on its neighbors. Okay, the neighbors are orthogonal neighbors. That means up, down, left, right. And a white cell that is not covered by any laser beam is said to be safe. and all the safe cells must form one closed circuit. That means forms a Hamiltonian cycle. So for example, here is a solution. Okay, here is a solution for a problem, and here all the safe cells here, okay, form a Hamiltonian cycle. All right, here's a program for the problem. So it first reads data, all right, into this is a matrix here, okay, indicates where heel cells are, and also the number of this hint numbers. So it uses a two-dimensional array of 0, 1 variables. So a laser named laser. Okay, so a cell is 0 if no laser kit is installed there, and a cell is 1. Okay, if there is a laser kit installed there. It also uses another two-dimensional array named road. So a cell is that indicates if a cell is a safe cell or not. So the constraint is installed this way. For a cell XY, okay, if it is not heel cell, okay, if it is a heel cell, then laser XY is 0. And also the cell cannot be a safe cell. Otherwise, okay, it first connects all the attacked positions, okay, attacked positions that are covered by laser beams from originating at XY. And for each such attacked positions, X1, Y1, so if a laser is installed at XY, okay, then this one is attacked, so no laser kit can be installed there. And if XY, there is a laser kit installed at XY, then okay, the cell X1, Y1 cannot be safe because it is attacked. And also there is a constraint that says, okay, if no laser kit is installed at XY or any of the attacked positions, okay, then the root XY is a safe cell. And the cardinality is okay, at least 1, because otherwise the runner has no place to stay. And also all the road cells, all the safe cells, okay, form a cycle. Okay, and the problem is the optimization problem. Okay, so the objective is to maximize the number of vertices in the subgraph. Right, actually in Picat, the attacked positions, sure, you can define this by using recursion, but you can, in a competition, in order to save time, you can connect all the positions by using list comprehensions. Okay, so a laser beam can shoot upward, okay, downward, leftward, or rightward. So, all right, the type of problem is well, again, also similar, giving a grid graph where some of the cells have clue numbers. Okay, the goal of the game is to color each of the cells black or white such that the following constraints are satisfied. There are no 2 by 2 black areas, and the clue numbers are respected. Okay, meaning a single number in the clue means one black block in the neighboring cells. In the neighbor here, neighbors, okay, the surrounding cells are considered neighbors, including the corner, okay, including okay the diagonal neighbors. And 2 numbers mean 2 blocks. Okay, the blocks must be separated by at least 1 cell. Okay, so here is a solution, and also all the black cells form a single polyomino. Okay, that means all the black cells are connected. So you see, the cells are the numbers are respected. For example, this 2, 4. Okay, you see this is a block. Okay, of 2 blocks, two cells, and also 4. 1, 2, 3, 4. Okay, a block of 4 cells. All right, here's a program. So it reads data, and it uses a board that indicates the clue numbers, and also grid, okay, a two-dimensional array of 0, 1 variables, and a grid. All right, well, this forms a strongly connected component, and no 2 by 2 black cells. Okay, this loop installs these constraints. And also the layout. Okay, so layout, it says constraint blocks. So make sure all the clue numbers are respected. All right, to get the neighbors. Okay, and each cell can have up to 8 neighbors, including the diagonally connected neighbors. So constraint blocks, it first find all possible layouts, so giving the clues. All right, and this is the neighbor, all the neighbors. It first finds all possible layouts. It's like inside this search problem, there is another search problem. Okay, so find all possible layouts. Okay, and then at least one of these layouts, okay, is the real one. All right, so it uses a Boolean variable for each layout. Okay, this Boolean variable means this layout is a real one, and then it uses this constraint. Okay, one of these layouts is a real one. All right, if of course, if no duplicates in the layouts, then you can change this greater than equal to equal. Okay, exactly one of the layouts is a real one. All right, we compared Picat with Klingo. Actually, for these problems, all right, the models for these problems in Klingo is quite straightforward. I mean, for reachability constraints, all right, and we compared 2 set solvers, all right, the KISS set, all right, and the Maple set. All right, the Maple set was a winner in the SAT competition 2018, and the KISS set was the winner of the 2019. Well, as you can see in the beginning, the problems were not easy to model in Picat. Some of the models we wrote took more than 1,000 minutes. That is way exceeded the time limit. Okay, by using these global constraints, all right, you can see all the instances can be solved in less than 10 seconds. Okay, using KISS set. All right, and for some of the problems, okay, the Picat models are significantly faster, okay, than the Klingo models. All right, here is an instance. All right, the hardest instance of the Roadrunner problem. So Picat solves this problem in in 7 seconds. All right, so basically, this paper conveys 2 messages. Okay, first, with these global constraints, Picat is a very convenient modeling language for graph synthesis problems. And the second message is with effective encodings for this global reachability constraints, Picat is an efficient solving language for graph synthesis problems. Okay, thank you very much.